I got this updated. Assignments. So tonight you have the vector fields is due at 7 p.m. And then tomorrow you have written homework, number 8, doing recitation, and then you have gradient fields, which we started talking about, we'll talk about today. That's due tomorrow at 7 p.m. Notice that's different, so that's Thursday at 7. Just so you have it done before the exam, because that's material on the exam. Okay, so this is all accurate on Blackboard. And then we have our exam Friday. So that's the same procedure as last time, which is you'll go to 203 right above here, and you'll start either at 11:15, it'll be 90 minutes, or you'll start at 11:45, it'll be 90 minutes. So I think everyone had either the half an hour before class or the half an hour after class free. If you've got the half an hour before class free, you'll come at 11:15, 203. If you have the half an hour free after class, you come at 11:45, 203. Questions about the exam? Yeah? What are the answers? That's the question that you can ask, and I won't answer. Any other questions? Okay, so gradient fields. What is a gradient field? Let's see here. So we're looking at this example, and we stopped last time. And so this was the surface, the multivariable function, x squared plus y squared minus 3, right? That's our standard paraboloid that opens up, but it's moved down 3 units, right? So its vertex is at 0, 0, negative 3. And then we said what's the gradient field for that? The gradient field for that is? Well, how do we make the gradient field? What do we do? Partial derivatives, right? So you take the partial derivatives, and that's the gradient, and when you do it generically for all x and y, that makes a vector field, right? It makes a vector field, and that's what I'm showing in blue. So how is the gradient field, knowing what the gradient means, how is the gradient field consistent with the surface? Right? That's the key question here. How is that gradient field consistent with this paraboloid? So why don't you talk to the person next to you for a minute. How is that gradient field consistent with or aligned with that paraboloid? Go.
You have the equations for the gradient about two x and y, right? So the bigger the x and the bigger the y, the bigger the gradient will be, right? Yeah. Which means as you increase x and y.
Okay, so I heard some good stuff coming from you. So what about the direction of these vectors? How is the direction of these vectors, knowing that they're gradient vectors, right? How is the direction of these gradient vectors, how is it consistent with this surface from which they came? Looking at the direction. Harrison.
If you're going outwards from the origin, you continue to use the greatest change.
Yeah, so if you think about this, like this paraboloid, anywhere in that paraboloid, the direction of greatest rate of change will be outward from the origin, right? No matter where you are. Okay, how about the magnitudes of these vectors? How's the magnitudes of these vectors consistent with that surface as gradient vectors? Christian.
It tells you about how much you're going to be changing.
Okay. Right. So how are those vectors then consistent with the surface?
So when it's closer to the bottom of the surface,
okay,
you can be moving as far up. But then once you get further out, it starts changing rapidly. So it becomes smaller.
Right. So down by the vertex, the rate of change it's less steep, right? It's like shallower. So those gradient vectors will be smaller. the further away you get from the origin, the steeper and steeper this thing becomes. So that your rate of change, your change in z, for a horizontal change is much bigger, so then those vectors are bigger. Does this make sense? So really, I mean, how did we get the gradient field from the original surface? What did we do? Derivative, right? So this is like the gradient field is kind of, as a whole, it's the derivative of the multivariable surface. You don't get a single function anymore. Well, you do. You get a vector function, right? So you get a vector field. But that is the derivative, and so this blue field is like the derivative of that function f, and so it's giving all the information about the rate of change. See that? So this is the derivative. This is the multivariable function version of a derivative. Right? So that vector field is expressing the rate of change everywhere of this surface, direction and magnitude. Okay, another example here. Let's look at this one. Okay, so here's the surface, minus x plus 2y plus 3. So find the gradient at 312 and 027, and sketch each of those on the xy plane. Go. Find the gradient at the point 312 and the point 027, and sketch each of those on the xy plane. So there are those 2 points. So
I found the gradient function to be -1, 2.
Okay. Then so then what's the gradient at 312?
Would it just be -1, 2?
He wants -1, 2. So did you sketch that? So okay, and what about the gradient at 027? -1, 2. So what's happening here? So can you describe what's happening and kind of make some connections here? Yeah, John.
The gradient's always the same at all points.
Okay, the gradient's always the same at all points. Okay, so can we make some then conclusions? Or a conclusion, yeah.
Well, if the original function is only a first order function, the
Right.
derivative is an order under that, and so it can be constant.
Okay, right. So we've got basically this is our linear version of a multivariable function, right? Which gives a plane, linear, and so then the derivative will be constant, right? And what does that mean? And what does that mean? The derivative is constant. Yeah.
Then all the vectors in the vector field are the same.
Okay, all the vectors in the vector field are the same. And what's the significance of the derivative? Right? What's the significance of the derivative? We have the derivative as constant. What's that?
Rate of change is constant.
Yes, this is our multivariable version of constant rate of change. What do you get? You get a vector field that's every vector is the same, right? So no matter where you're at, the direction and magnitude of max rate of change is the same. So this is the multivariable version of constant rate of change. What's the single variable version of constant rate of change? What do you get with single variable function when you have constant rate of change? Yeah, it's like a linear function, and then the rate of change is horizontal line, right? So that's the single variable version. You have any line, its rate of change is a horizontal line, constant rate of change. So then this is the analogous situation for a multivariable situation, or multivariable function. Constant rate of change. Okay, how about this one? So I'm just going to show you this is in the xy plane, this is the gradient field. So can you describe what you're looking at here? So this isn't hard. You can do it. Go. What is the function like? Can you describe what this function is like if this is its gradient field? Go. Talk about it.
Yeah.
Okay, let's see what you came up with. So Ethan, tell me one thing that you talked about or observed here. Okay, hold a sec.
So the top part, the arrows are all like pointing towards the middle part to kind of be like an upside down parabola.
This one?
Yeah, that part.
An upside down parabola. Okay? So instead of trying to say like which, yeah, so what would this mean? That all the arrows are pointing into a point? So you said it's a maximum. Is it a maximum? Yeah, so you got a local maximum here, right? Because everywhere is pointing in the direction of max rate of change is pointing to this point, so you're going uphill all the way to there. Okay? Tell me something else. Andre, anything else you want to say?
It's like the exact opposite for like the
Bottom left. So what do we got here? Local min. All right. What's going on here in the second and fourth quadrants? The saddle? Because in this direction, what do you have? Right there. Minimum, but in this direction, maximum. So these are saddle points. Okay, so we've got this kind of checkerboard of local mins, local maxes, and saddle points. What will that, anyone put that all together? What will that kind of be like? Like a bumpy kind of thing. What's that? Like hills. Like hills. Okay, here's the... where'd you go? There we go. So here is I could have had you draw. So this is the gradient field and the contour plot. Right? So these are contour lines, lines of level curves, lines of constant z. And remember the direction of the gradient was always orthogonal to level curves, right? So here's another view of it. So actually, we said that there were 4 representations of a multivariable function, and now we have a fifth, right? So now we have a fifth way of representing a multivariable function, and that's with its gradient field. Okay. So here's the gradient field and the contour plot, and then here is. So we're going if you zoom out. So this is actually the sine x plus, what you were looking at was sine x plus sine y. So it's an egg carton. Okay. So then, that's kind of the idea of like visualizing and thinking about gradient fields. Really, a gradient field is really the representation of the derivative of a multi-variable function by giving you the rate of change, the max rate, or the rate of change and direction of rate of change at any point on the surface as a vector field. So then the question becomes, if you have a vector field, is it a gradient field? So are all vector fields gradient fields? All right, so suppose I said that the gradient field, so I have this vector field, I can't call it a gradient field, but I have a vector field. 2, y. Okay, we could sketch that, analyze it. There's no gradient field or vector fields are. So the question is it a gradient field? And if it is a gradient field, then what is 2? What does it represent? The partial derivative with respect to x, right? So we're saying, is that the partial derivative with respect to x of some function, and the partial derivative with respect to y of some function? So really, from each partial derivative gives us a potential, it gives us a different perspective on what this function f is. These are not 2's, these are question marks. So from the partial with respect to x being 2x, we get a particular perspective on what f could possibly be. And so what could it possibly be? That 2x would indicate what? Sorry, 2. That 2 would indicate, if that's the partial with respect to x, it would indicate what about the original function? That you have a 2x, right? Could there be anything else in that function? Yeah, so plus c. But, so yeah, so plus c, like meaning like just a constant, but there could be something else too. Yeah, there could be some function of, so I'll call it some function of y, any function of y, right? Because that would not show up. If you took the partial derivative with respect to x, you get the 2, this would go away, right? So any function of y plus any constant could be possible. So just knowing that the partial with respect to x is 2 gives us this perspective on what f might be. And then knowing that the partial with respect to y is y gives us another perspective on fxy. I'm not writing a second function here. I'm writing the same function, but a different view of it, right? Because both of these partial derivatives came, if it is a gradient field, they both came from the same function. So this is like perspective number 1 on the function, from the perspective of knowing the partial with respect to x, and this is perspective number 2 of the same function, right? Knowing the partial with respect to y. So if the partial with respect to y is y, then what do we know about the function? Y squared over 2, 1/2 y squared, right? 1/2 y squared. But then there could also be function of x and... So if this is a gradient field, then it needs to be possible that these are the same function. I'm not going to add them together, right? They're the same. So is it possible, based on the information that we have, that there is one function that meets both of these criteria? Yes. Okay, so this should be able to see that. It's pretty easy. So why? Because 2x matches up with this h of x, right? And? One half y squared matches up with g of y. So it's a perfect match, right? It's a perfect match. Therefore, the potential function, and then we could have any constant, right? Any constant. So therefore, the potential, so given a gradient field, the function from which it's called is called the potential function. We can write it. What is the potential function for which the given vector field is its gradient field? What would it be? 2x plus 1/2 y squared plus any constant. And how do we check it? Well, find the gradient. Take the partial derivatives. If we get exactly what we started with, and we do, we get 2 and then y. We got it right. Okay, another example. So. How about this one? Y comma 1. All right, so we're going to do the same thing. We're going to say if it was the gradient of some multivariable function, then its partial with respect to x would be y. And what view of the function would that give us? We'd have a term xy, right? And then we could have function just strictly of y that we wouldn't see in the partial with respect to x and a constant. All right, and then another perspective on the exact same function would be from the information that the partial with respect to y is 1. And what view of the function does that give us? Y plus some function of x. And these could be 0. So there doesn't have to be, all right, just so you know. They were just accommodating for all possibilities. There could be no term just function of all y, and there could be no function of all x, but we just have to accommodate for the possibility, okay? So if this is a gradient field, then these two have to be resolved as the same function, right? These are just two perspectives on the same function f. Can you do it? Possible? Hem.
Wait, so why do you have to do it in 2 steps instead of just write that as y equals something? Like why do you have to say g of y each of x instead of saying x times y plus y?
I think maybe your question will be answered when we keep doing this here. So this is all you know about the function. If this is how you could write the function if the partial, knowing only that the partial with respect to x is y. And this is how you would write it, knowing only that the partial with respect to y is 1. So if this is a gradient field, then these two need to be the same function, right? Then these are the same function. You can resolve this as one function. Can you do it? Well, I've got a function of y here. That's good. Do I have a function just of x up here? That's fine. I can just make that 0. That's fine. Okay. And what about the xy? Yeah, there's nowhere down here. There's no place for xy to go. Right? Conclusion? Not a gradient field. This is not a gradient field because you can't make these the same. These are not the same function. There's no xy down here. There would need to be an xy down here. So you can't write, the point is, you can't write a function f whose partial with respect to x is y and whose partial with respect to y is 1. It's impossible. Why not? So why is it impossible? Because what would the partial, if it had the xy term in it, what would the partial with respect to y be? you'd have this x in here. There'd be an x in there, right? You don't have any x's in your partial with respect to y. So as long as you have that x, y in there, your partial with respect to y is going to be a function of x. But here it's just a constant. Can't resolve. So y1 is what? Not a gradient field. So of all the vector fields, are there more gradient fields or non-gradient fields of all the vector fields? Why? I'm just guessing. Yeah.
You can just make a vector field for every constant of 1, right?
Sure.
Like I can make 1 any like random constant and still not be a gradient field.
Okay. Yeah. So yeah, you gonna say?
Well, I was gonna say, isn't there only one like greatest rate of change? Or would that not like play into effect here? Like, so you can only get one gradient field from a function.
Right. So for every function, there's only one gradient field. But the question is, if we looked at all possible vector fields, like two-dimensional vector fields like this, would you guess that most of them are gradient fields, or half of them, or most of them are not gradient fields? Most of them are not, right? So gradient fields are very, very, very special, right? Because they follow they have this pattern of partial with respect to x and the partial with respect to y of some function. So the vast majority of vector fields would not be gradient fields, okay? So gradient fields are special, right? They come from some multivariable function, which we call the potential function. But if you had the whole set of all vector fields, like very, very, very few of them would be gradient fields. Okay, any questions on that? Yeah.
Well, what if you said like that there's an infinite number of vector fields?
What's that?
Are there an infinite?
Oh,
number?
sure.
So
Sure.
if there's like even 1% of all vector fields are a gradient field, then isn't there an infinite number of gradient fields also?
Sure, because yeah, sure. So now you're talking about like cardinality, right? There's different sizes of infinity.
Oh yeah.
So that you're getting into that now, that's absolutely true. Yeah. In fact, the percentage of gradient fields is compared to all vector fields is like 0. So that, you can wrap your head around that. But there's an infinite number of gradient fields, like you said. How is it possible? It's true. Okay. It's kind of like it's like comparing the irrational numbers to the rational numbers. There's an infinite number of rational numbers, but if you picked a real number, the probability that you pick a rational number is 0. If you pick a real number at random, you'll always get an irrational number, even though there's an infinite number of rational numbers within the real numbers. I'm not making it up. It's true.
You're saying that for one function, if we have a vector field for one function that has infinite gradient fields?
No. I'm saying you start with the set of all vector fields. Yeah, if you have a multivariable function, it has one gradient field. It has one rate of change function. But I'm saying start with a set of all vector fields. Of all those vector fields, like essentially 0% of them are gradient fields. Even though there's an infinite number of gradient fields because there's an infinite number of functions that you could dream up, right? Okay. So let's talk about line integrals. So line integrals of multivariable functions. What are we talking about when we say line integrals? Okay, they look like this. So let's identify the meanings of all these things. These are all things all these symbols are familiar, just never all together. Like this, all right? So let's talk about what things mean here. So what is fxy? What is c? What is ds? So if you think about maybe an illustration here. So for my illustration, given what I have, would I be drawing this illustration in R2 or R3? He wants R3. Agree? Yeah, we're going to draw in R3. Because what is fxy? Multivariable function, which graphs as a surface in R3, right? Surface in R3. Okay. What is C? So we're gonna integrate this multivariable function for a certain set of points or over a certain set of points, which we call C. Have we used C to mean anything in this course so far? Was that? Yeah, I think we did, right? What was C? What's that? Is it a region in XY? It's an XY, but it's not a region. A curve, right? So it could be a line. Lines are curves. So C is some curve. So we're going to integrate this multivariable function, but only for the points C in the xy plane. So what is ds? That's from Calc 2. Who remembers what ds is? So this is our surface. This is our curve in R2. So remember what ds stood for? Yeah. Arc length. Yeah, it has to do with arc length, right? So having to do with arc length, what is it? Yeah, Alex.
Change in curvature.
It's not the change in curvature. Anybody remember what ds was? Like a little bit of. Yeah, it's just a little bit. It's a little bit of arc length, right? So it's a little bit of arc length. So it's a little. ds is a little, just taking a little step along the curve of C. So what is this going to find? Because you can imagine what this will find based on our understanding of integrals. So we're going to integrate the surface, but only for the points of C. And then it's going to be the z, each z value times a little change in arc length, right? So this is like the z value times a little ds. So like ds is like a little change like that. So if we accumulate all these, what, z times ds's, what will that give? Yeah.
Is it kind of like a sheet of paper that occurred?
What about the sheet of paper?
It's like, I guess call it the cloth. So like the bottom of it is going to be the curve.
Okay. He's talking about something to do with like a cloth or a curtain, whose bottom is curve, length, and the top is surface. And what about that cloth? So that's an object. Mathematically, what will this be? So it'd be like the area of that curtain, right? So it's going to be like the area of that curtain as we sum up or accumulate all these z values times little changes in the arc length. We're going to be accumulating the area, right? Will it necessarily be area? Net area, right? If that function, again, if that function, we've talked about this before, if that function ever goes below the xy plane, those areas where the curtain falls below the xy plane get subtracted off, right? So it's going to be like net area. So ds a little bit of the curve of C. So we've got s and x and y, but we have a single variable or a single integral. So if we're going to have any chance of solving this integral, we've got to resolve this all into a single variable. So what might that single variable be that we could resolve this? If we've got the curve C in the xy plane, how did we write curves? Remember? Remember how we... Well, single variable functions give curves, but we also learned a different way to write curves. Anyone remember? Yeah. Yeah, vector, right, single variable vector function, right? Remember those? R of t gave us curves, right? If you put all the vectors with their in standard position and let t change, you get a curve, right? Whether that's in the xy plane for a two-dimensional vector or in space, three-dimensional, we get a curve. So what we can do is we can write this whole integral in terms of t. And by writing it all in terms of t, then we could solve it because we have a single integral with a single variable, t. Okay, so ds dt, what would ds dt be? It'd be the rate of change of arc length per change in t. So it's the rate of change of length, the length of c for a small change in t. So we saw a different way to express that when we worked on vector functions. When we worked on vector functions like this, how could you get the rate of change of the length of c for a small change of t? Anybody remember? Or we could get that from, say, r of t. What's that? The derivative? Okay, so something to do with the derivative. Is it the derivative? Now, the derivative is going to be another vector function, right? R prime of t. Right, so this is really talking about isn't this the magnitude of the derivative of our vector function? Or like speed, right? So the derivative, r prime of t, would be like a velocity function, and then the magnitude would be speed, and that's exactly what ds dt is. It's like speed. So ds dt is like the magnitude of the derivative function. And so this gives us what ds is. Then what is ds? Oh no, don't do that. If ds dt is the magnitude of r prime, then ds is? Right. Then ds is the magnitude of r prime t dt. So this is how we can then start writing this in terms of t. Drew my picture in the wrong place. So then we can take the multivariable function and we can write it in terms of t by making x of t and y of t according to whatever r of t is. And then ds is the r prime magnitude of r prime t dt. And then we'll integrate from t1 to t2. And so now we can actually solve that because we got a single variable function and a single variable. Okay, any questions about any of that? Okay, so we'll just do this kind of easy example. So we want to find the line integral of x ds, where c is the arc of y equals x squared, from negative 1, 1 to 3, 9. So let's draw that, first of all, in the xy plane. From negative 1, 1 to 3, 9. So that's our C. So what we're going to need is we're going to need the parameterization of C, meaning we need the vector function for C. So we did this, whether you might not remember, but we did do this. So how can we parameterize C into a vector function so that we get these points on the graph of y equals x squared? And t squared. Remember this technique that if you don't have something in a circle, something circular or elliptical, you can just set, like, if you have y equals x squared, then you can set x equal to t, and therefore then y will be x squared or t squared. All right, and so then what do we need? We need x as a function of t. What is x as a function of t? It's just t, according to our vector function, right? And then what was ds? ds is, what we just showed, is the magnitude of r prime of t dt. So what's r prime of t? One, 2t, right? So what's the magnitude of that? Right? 1 plus 4t squared. So my x, according to the vector function, my x is t. My magnitude of the derivative is the square root of 1 plus 4t squared. And that's my ds right there. And then t will go from what to what? So here we're going from negative 1, 1 to 3, 9. Then t goes from? T is the same as x, right? So it's going to go from negative 1 to 3. And that we can solve. I went a little bit faster, so did you catch all this, what we did?